This is the installment in the 4C webinar series. Today, our speaker is James Shinkle of Optical Scientific. He'll be talking about two-dimensional wind measurements with LOA technology. With that, James Shinkle, take it away.
Thank you, Steve. So can everyone see my screen?
Yeah, I can see it.
Great. Okay. So what I'll do is I'm going to go over where LOA came from and kind of how you can use it along the fence line. There's a couple of different ways that you can set it up. So we'll just jump right into it. We're calling it Understanding the Fence Line Using Large Area Two-Dimensional Wind Measurements with LOA Technology. And if anyone's familiar with our OFS technology, OFS was developed from LOA. So LOA was actually our first system. It was developed by environmental research labs in NOAA in the 1970s. It simultaneously measures the average wind across the optical beam, so the cross, and then also measures the turbulence, which is CN2 over the measurement path. So the turbulence is mostly used for airports and wake vortex and stuff like that, but it has those two measurements that you can use. The path average wind sensors offer vast improvement compared to like a single point wind sensor for large area wind studies. It offers a more spatially representative measurement compared to like a single point sensor. So you can have a single anemometer and you can have another one 10 yards away and it'll read something completely different. So what's nice about LOA is we can shoot up to 9 miles and it measures the average wind speed over that 9 mile or that distance, those 2 points. So it's a single point measurement, or not a single point measurement, but a spatially averaged measurement over that whole path. It's truly versatile, so you can use it in a lot of different ways. So I'm going to kind of go through some of the advantages of it. It's path averaged, as I mentioned. It's completely eye safe, so you can operate this in public areas. It's portable, so you can set it up on tripods or up on top of a roof or shoot it through a window. It's easy to set up and hooks to a laptop, or if you want to connect it to a network. It's long range, so I have from 200 yards to 6 miles, but we can actually go up to a little bit further. It has Modbus RTU or a simple ASCII string that can be common to limited format that you can power into something. It can be powered by AC or DC, so if you want to do a car battery, if it's in a location you don't have power, you can do a car battery. They can be placed in safe areas away from hazards. So again, you can put it up on top of a roof or shoot it through a window or on top of some sort of roof or exactly. So it can measure up to 10 kilometers. It measures bidirectional wind, so we're measuring the crosswinds across that optical beam. If you set up 2 LOAs in like an X pattern, it'll give you both the x-axis and the y-axis, so you can measure the magnitude and the wind direction of the wind vectors. So think of it almost like a giant anemometer, where we're measuring that wind going across this plane, and then if there's a significant change, we can pick that up. If you use 3 or more LOAs, you can form either, if we do 3, we can do an equilateral triangle around the area of concern, and then account for the movement of that air in that large space. So what you could potentially do, if you don't want to surround the entire refinery, maybe you want to surround an area of the refinery or certain processes, we can kind of set up wind vectors around that space. We do have retroreflectors that you can put on towers and stacks to measure vertical wind profiles, but I'll show you how a lot of that doesn't really change. We use that for measuring wake vortex, but we do have a smaller version that uses a retroreflector. Again, we can shoot from buildings, out windows, or over water. This is just kind of an example of an LOA mounted on top of a trailer. We were doing wake vortex for a NASA study at airports, so that just gives you an idea. So when I was talking about measuring surrounding an area of concern, when you use several LOAs to form an enclosed contour, at each lag, it'll measure the crosswind along that optical path. And then by averaging those wind vectors on all sides, it'll give you an average two-dimensional wind over that large area. So in this, we would see everything coming in from here. You see we're shooting over the river. You get everything coming from here, everything going out. So this is bi-directional, but we can see everything and anything coming into this area of concern. So we kind of have our own little meteorological area of concern that we can do. So surrounding an area of concern is important. Now, if you just want to put a barrier between one plant and another to figure out, hey, we think that the pollution's coming from that area, you can always just set up a single anemometer and then know what is, or a single LOA and know what the average wind over that large space is. When you think of the capabilities of LOA technology, it's kind of like micrometeorology. We can do convergence and divergence diffusion studies. That gets a little bit more complex and probably more than you need to really do for these types of applications, but we do have that capability. You can obtain a two-dimensional wind profile. We can measure updrafts and downdrafts, but that's more for when you surround something. So if you're seeing wind going all over. They use it for plume dispersion for the military. So the military uses LOA when they're doing weapons dispersion modeling. We measure crosswinds. Yes.
I don't think your screen is updating. You may need to click on those slides to get your screen to update.
Okay, where are we at right now? Do you see LOA technology capabilities?
No, you're on surround area of concern, your first slide.
You know what? I think it's just probably going slow, so let me let it catch up. You see LOA technology now?
No.
No, slide 12.
Huh.
Oh, can the others see the slide, the updated slides?
No,
No, I can just see slide 12.
Yeah, slide
Sometimes
12.
if you close it out and reshare, that might
Okay.
update quicker.
Let me try that. Yeah, a second here. Okay, can you see it now?
The
Still
main,
slide 12.
Yeah,
main-
still slide 12.
Do you see this one right here? You know what? I think I know what's going on. Hang on.
Yeah, I think it's the specific window you shared, maybe.
Yeah, you know what? Give me 1 second here. Give me a second here, sorry. Huh. Give me one, you know what? I'll shut this down and then do you see my main screen now?
Nope, still see surround area concern.
Yeah, I think Jackie was right. I think you shared some different screen than you're trying to work off of.
Yeah, let me see here. Okay. Okay, now do we have understanding the fence line?
yes.
Yes.
Okay. All right, sorry about that. You know what? I think I had two of them open, so I apologize about that. So there's this surround area of concern. You're seeing that?
Yes.
Okay.
Yes.
All right. Sorry about that. Technical difficulties. Okay, so this just kind of talks about how we can do the crosswinds or plume dispersion modeling, measuring vertical profiles. It just kind of talks about the different capabilities you can use LOA for. When you think about optical scintillation, it's basically fluctuations in light and then temporal cross correlation, so time of flight. So if you think of when you look up at a star twinkling, you see that temperatures in the air cause scintillation. So that's what we're kind of measuring, is that thermal turbulence in the air, which in the detectors are like 6 inches, so we can pick up little changes. So you'll see these pockets of air that go by. It's the same principle that we use for OFS technology, but just on a much larger scale. So as these plumes go by, we pick up these data points, these shadows that are caused on our detectors, and that we take 4,000 sample points every 0.3 seconds. And then that you'll pick it up in detector A and then a detector B. Because it's bi-directional on LOA, it goes both ways. So we'll pick them up in B and A if the wind switches the opposite direction. This is just kind of a diagram. I'm going to whip through that one. Some of the successful applications that we've had that I think you'll find interesting. This one is just, I put it in here because I thought it was interesting. We have, we measure the roof vents of aluminum smelters. So that's like, we developed this specifically for them, and it does like a 3-kilometer range, but it got Method 4 approval. This is the one where I think you'll find interesting when we talk about path averaged wind. This is a paper done by Dr. Wang and a few others. And in this one right here at Table Mountain, what we did is we looked at a section between Denver and Greeley to watch pollution drift. And what we did is we shot this over a number of miles, and we had to compare it to 10 different anemometers. So you see the average of the optical measurement up here, and then the average of the anemometer readings. It was kind of difficult with the anemometers because they were kind of jumping around, but the path average gave us a good reading that the LOA does work, and it gives that. This other one is where I think things start to get really interesting when you look at LOA. In this study, what we did was we had a Met tower with different heights. We had different anemometers at like 10 meters, 50 meters, and 100 meters, I think it was, or 75. And then we surrounded that with 3 LOAs and formed a 450-meter equilateral triangle around this meteorological tower, which is 300 meters. Then we had a bunch of PAM stations that were located in this area as well, and those were portable automated mesonet stations operated by the National Center for Atmospheric Research. So it was doing wind speed, wind direction, pressure, temperature, humidity, and a few other parameters. So we're comparing all of those in this study. And what we found was this scatter diagram showed that there is a linear relationship indicated by the solid line between the 2 measurements of wind speeds and the optical triangle. So we could see that there was a linear relationship with our measurements around this Met Tower station. Where it got really interesting is when you look at the horizontal wind and the spatial variation, the difference between the tower and the optical data becomes really significant when you look at the spatial variation of wind velocity and where it's really large. So trying to study large bodies of air is really difficult with a single Met tower, or for that matter, you were saying, Jackie, trying to measure it from a Met tower that's 20 miles away. Or however far away it is at the airport. So if you look at this on this little thing, you can see where we have the optical tower, the optical measurements, the tower, and then the PAM stations. And you can see where these, when we're looking over a long distance, you can start to see where the spatial variation and how much wind is going to actually make a difference in your measurements or your calculation of what's going on in that area. So this is another scatter diagram that we did of the wind measurements at 10 meters versus the optical measurements, which are kind of at ground level. So the agreement's good, but it's not perfect. But this is just showing that we still kind of can give you a good measurement. The wind speed's going to be much faster the higher you go in magnitude towards the ground and up. So we're measuring below the inversion layer. Now, here's another study that we did where it was done at the Inland Empire, and it was a composting site. And what they did is they compared, the LOA was a little bit too long, so we modified an OFS, and we compared it to, we used it along with a TDL from Boreal Laser. And that was our direct measurement. So we measured NH3 and CH4, and then the wind directions. And then there was one thing that we noticed is wind is seldom constant. So they had a radiometric measurement, and that was assuming that wind was constant. So when we get into some of the data, you'll see that their results were actually much higher than the direct measurements that were using LOA technology and a TDL. So when we get into this, at the start of the site, you'll see that, and I'll show these screens in a second, the wind was blowing north at like a steady 2 to 4 feet per second. However, about 3 hours in, the wind died down to 0, and it stayed calm for about an hour. And then towards the end of that measurement period, the wind is going to reverse completely direction altogether. And one of the major advantages of LOA technology is that it measures the true crosswind average across the optical path. So therefore, the flux through that measurement path is not affected, even though the flux through other directions might change. So this just shows kind of a graph of the wind speeds and wind directions that we were watching through that optical path, and you can see it kind of change. When you get into the measurement data here, you'll see the radiometric method and the direct measurements. You know, they're pretty close. The gas levels are a little bit higher on some of these areas. Like when it's high, it's a much higher, and when it's lower, it's a little bit lower. So the measurements are a little bit different. And what we found was when you compare the wind data to the source concentrations, they seem to be higher with the lower wind speeds. So when there's no wind, the concentrations were going up, and those differences in the low level measurements was the wind was steady, right? So when there's a steady wind, you have wind that's blowing the concentration of the gases across. When you have no wind, it just kind of sits there. So during that middle time, the wind was mostly 0 most of the time. So you had these spiking effects from the if you look at this one right here on the methane, it's a lot higher compared to the direct measurement. So they had a system that was assuming constant wind, but the rate of the VOC gases dispersion will depend on the wind. So during low wind concentrations, the gas can't disperse, so the gas concentrations can build up. And that's what we kind of proved. So it just shows that if you're measuring wind more accurately, you can kind of get a better idea of what is actually happening. With the optical system, what we did here is, here's Sung, he's out in a truck and he's shooting up at this retroreflector. So we put one at 12 meters above the ground and one at 1.5 meters above the ground. And what we did is we did a crosswind analysis to see if the agreement of crosswind at higher and lower planes indicate that the crosswind is really not that sensitive to measurements, if they're higher or lower, right? But when we looked at the turbulence, what we found was when you're looking at, we switched the detectors here where we were shooting at the top, you know, at unit number 2 is in blue and unit number 1 is in red. So when we flipped them, you'll see how that was different. So it basically showed that when you're looking at CN2 data, which is turbulence or wake vortex, then that measurement of shooting up higher is actually a lot different than compared to the crosswinds. Again, I don't think the turbulence is going to be much importance to you guys. It's more the crosswinds, but I just wanted to show that slide to kind of give you an idea of what the instrument's capable of doing. So when you think about LOA technology and how to use it, we're measuring crosswinds and averaged along the optical path. So therefore the flux through that measurement path is not affected, even though the flux through another direction might change. So LOA, when is an optical instrument, it can be accurate and measure the spaced average 2-dimensional wind velocities over that large area. These spaced average 2-dimensional wind measurements are more representative than like a single point wind measurement. If you're trying to do a single point wind measurement, you're never going to be that accurate or understand what the wind is doing, because it may be bouncing off of the building and saying the wind's going this way or that way. With LOA, because it's path average, you're getting a more representative or spatially representative measurement of wind across that path. When you use 2 LOAs in like an X pattern, we can measure the magnitude of the wind direction and the wind vectors. So it's kind of, you know, again, like a giant anemometer. And then when you're looking at the spaced average horizontal wind velocities, they can be obtained from the wind measurements of the 3 sides of a triangle. So that's, you know, if we look at surrounding a facility or surrounding an area of concern or a process, we can surround it in a triangle and then kind of understand what the wind is doing around that process and where that's going. if you combine LOA with other sensors, it'll help you better understand the mass movement of hazardous wind. So, you know, a lot of people are putting up just single point sensors, or sensors that they, that they put on the fence line, and then they come back 2 weeks later and they send it in for a test. I think a lot of the TDL guys or the DOAS guys or the open path guys are saying, hey, we can give you a measurement in real time and tell you when you're having, when that's actually coming, when you're actually having that problem. So with LOA, if you put it along a fence line, you'll know what the wind is across that whole path. And you only need about a 2-foot area that we can shoot that beam through across that distance, however long it might be. So that kind of sums up how you can use LOA. And then this is our users list. You know, we work with the military mostly, and Alcoa, and a lot of the aluminum smelters, and Navy research. A lot of our stuff is government funded research that we use for us. And then these are just kind of the references, the papers. I can always send you those papers if you want to see them. Some of them are a little technical, so unless you're a meteorologist, it's going to be hard to understand, but we could always kind of go into more detail if you need to. And then this is the SBIR. This is the stuff that we did for NASA for the wake vortex. So in a nutshell, that's kind of what LOA does and how you can apply it. So I tried to keep it kind of tight here. Does anyone have any questions?
Yes. So I'd have a question. Would LOA help if you have fence line readings, quantify those, or help locate the emission source?
That trying to figure out where that emission source is. We have another system called Hazmat, which is like a portable little what do I want to say, anemometer that you can move around inside there. LOA is more, what we're doing with LOA is we're putting a line measurement across a side to figure out, okay, the wind was coming from this direction across this line most of the time. So if the wind is blowing towards your plant and you're getting fined, you would be able to know whether or not that wind was coming from a different direction and blowing into your plant. So if it's blowing towards your plant and your sensors are picking up right there, we would tell you whether or not that wind is coming from, what direction that wind was coming from over that long path. So if you have a bunch of sensors and you're like, it's coming across here, then we would measure that. Does that kind of help measure that? You're trying to get more specific to pinpointing the actual point of where the source is what you're saying?
Yeah, I think what you're saying is this would give you accurate wind direction. So if there's an emission or a complaint, you would have very valid data to know whether that the wind was in the direction of the complaint.
Right. So like on here, if we have wind coming across this line right here and your plant is right here, then we're going to say, but there's another plant over here, another source, but where you're getting your fine is from this line, and you notice that the wind is predominantly coming from another direction. If you pair that with another sensor, you'll be able to determine whether or not that is actually coming from your facility or from another facility, I would think, or give you a better idea. You can do a single anemometer in one spot, but to try to use a single anemometer to understand a long area like this, the wind can be different 5 feet, 10 feet down. Just by the way, the nature of it, you might get like a gust you might get a gust over here and not right here. So you might get a big gust here, pick that up, but over here it's kind of dead wind, whereas LOA is going to average that whole area across that line.
And you used flux and turbulence. What's the difference between flux and turbulence?
Well, turbulence is going to be like the turbulence in the air off of like when you have an airplane take off, what you'll do is you'll have this turbulence, the wake vortex off a jet aircraft will actually throw the air up in the sky, right? It'll twirl everything out. So we'll actually measure that turbulence. The flux is going to be how much gas is going across that plane, or how much that gas is going across that area. So if you like, the flux won't change if the sometimes it won't change in one area, but it'll change in another area. If that, I'm not sure if I'm explaining that well enough.
No,
Because you're trying to look at like, so you're looking at this area, like your plant, and you're trying to figure out like, okay, how much of the gases that are in this area, this spatial area, are going this way, or are they going this way? Are they going towards this population here? Is the air coming in here to our plant from another area? So with LOA, what we're saying is we're going to give you a more spatially representative idea of what that wind is doing across this plane. And that plane's bidirectional. Now the question becomes is how you set these up. Do you just do a single plane and then add another line here to see if there's a significant change? So if you're looking at, a fence line and you're wondering, hey, I want to know if gases are going towards that facility, or towards a population, I would, with LOA, I'm going to know across this entire plane what the wind is doing, because like I was mentioning before, if you have a wind gust, you can have a wind gust through one part of this, but maybe it's not all the way across. So if you have an anemometer there, it may say, hey, it's blowing this, and you may get a higher concentration with a single point a concentration analyzer. But with this, you're getting an average wind across that whole area. So you're like, okay, this is how much wind and how much of that pollution is going across that whole area. Now, depending on if you pair it with like an open path gas analyzer, or maybe a GC that's sampling every 15 minutes, or if you're even using, the tubes that they use for measuring benzene, you could then look at the wind data across that fence line. So if you're like, God, the benzene levels are really high along this fence line, then you can start to kind of figure out like, okay, the wind was blowing in the opposite direction towards our plant. So are those benzene, the problem you have with those tubes is they're an average over 2 weeks. But if you have an open path gas sensor, we can say, over this whole area, the wind was blowing towards our plant, and it was bringing that benzene towards those tubes. So that's why those measurements are reading. Or if, for example, I believe if you have no wind, so let's say it's just dead area or dead wind, and you have benzene just kind of building up in that area, I don't know how that would affect those readings on those tubes. Is that if the wind's blowing, it's dispersing. But if it's not blowing, it, the concentrations can kind of build up. So are they building up and being higher in that area because there is no wind? Now, if that's on your side, maybe that's a problem. But if it's, from the other side, maybe it's not.
Oh, no, James, we're doing an odor source, or an odor source identification and study. And it's amazing that the odor calls almost always happen after a period where there's no wind for 6 or 8 hours. There's no accumulation of material, and then there's a wind that picks up and moves that cloud over a community. So it's a combination of no wind, then there's wind. Yeah, I would see, and if you scroll back to the numbers that showed the magnitude, the order of magnitude of those numbers.
Oh yeah, I got that.
So I do lots of these webinars, and occasionally I'm surprised by some data set here or there. But that data set,
so like during the middle time, there was actually that's when the wind died off. So you see this radiometric method, when the wind died off, the concentration really went high. But when you're looking at the direct measurement that's saying, okay, that the concentration in here is really high, but over here where there's no wind, it's actually lower. So you're not that concentration is staying there, but it's not actually going across that path towards that community, that measurement path.
Correct. In that you're an order of magnitude difference here in the middle between the radiometric and the direct. And most of these facilities, an order of magnitude is way beyond the amount of error they would be willing to accept. So if they're using wind data in combination with concentration to calculate the mass going across their fence line, what this data tells you is they may be overestimating by 10 times if they're using a single anemometer to do those calculations.
Right. And even if you use like you can have single anemometers, but if you even try to use a whole bunch of different anemometers, anybody will tell you it's very difficult to try to understand that with just those single or just a couple of them, because the wind can be so different. And that's one of the advantages of LOA, is that it's path averaged. So we know what's going across that optical path. And then the question becomes is, how do you want to, one thing you got about OSI is like, it's a sensor. So we're building it as a sensor to become part of a network. And then if a facility's like, hey, I want to use this, then we can kind of tweak it to figure out how they want to use it. Like, how do they want to use just one across one line just to say, hey, I want to know if it's coming from that plant or ours, so I have a fence line, or do I want to do, enclose something and kind of get that, I think it was right, where is it? Where they show this one, where they show the triangle, so I can get that equilateral triangle. I know the 450 meter area within here, what that wind is doing. Is that wind going this way? Is it going that way? When you look at a single point, you're only looking at a single point. But when you surround an area, you can kind of say, okay, here's this big pocket of air. I want to know what's going in and out of that. It can get a little expensive, but it can also maybe be paired with something where it makes more sense. So it's not going to be, it's not meant to replace anemometers, but it's meant to be used as another tool that you can use to better understand what's happening across those fence lines or across an area, or what's going on with the wind.
Yeah. And an anemometer will tell you what is happening with the wind speed at that exact point, whereas your technology tells you the flux across the plane, or if you put 3 of them, it would be the flux through a volume. Right.
And when we did the one with when we did the one with the South Coast Inland Empire, we were able to kind of use it we used 2 modified sensors, and we did one perpendicular and one parallel to indicate when there's a significant change in the wind happening. So that was one way that you can set up. So there's a lot of different ways that you can use it. We would kind of meet with you or meet with the facility and then kind of help them determine what they want to do. Now, OSI can build weather stations, and we can also do met towers and create. We do a bunch of stuff for airports. So we build weather systems to kind of understand the weather around an airport. So we could obviously get into more detail and look at weather kind of around a facility. It depends on how in depth you want to go. But definitely, if you're looking at trying to understand what's happening across a plane, LOA technology will give you a really good representative of what's happening in that area. And if you're using, I've always kind of felt that it kind of validates open path gas sensors, because when you use an open path gas sensor and you're getting the concentration of gas across that whole plane, you might as well get the wind across that whole plane too, to see, okay, what's happening across that whole plane.
Yeah, if you pair this with fence line monitoring, like an FTIR type fence line monitoring, then you could get a much more accurate quantification across the fence line.
Right. You could look at the mass emissions across in that whole spatial area.
Yes.
But they're not going to tell you, like EPA is not going to tell you that you have to buy one of these. And I don't think that they necessarily should. I mean, it would be great if they did, but I don't think that it's more to, like, most of the people that have bought LOA or any of our sensors have been companies or industry that's come to us and said, hey, we really want to understand what's going on. So they go to EPA and say, we want to test this. Like, EPA has one of these. They have an older version, and then NASA has like 3 or 4 of them. So, you know, doing a study is not a bad idea to kind of figure out, like you were saying, like, are you overestimating or underestimating the amount of pollution going across your plant or across a line? Because if you're overestimating, you're paying probably more, or you could potentially get fined, I suppose. So kind of understanding that this technology, if you were to go to EPA and say, hey, I want to throw this in with this open path gas sensor, then we could give you a better idea of what is actually happening with that air in that space. And they can feed, you know, you can feed one into another. So you can feed one LOA into another, and then send that all in one string out to, you know, whatever system that you need. And then if somebody wanted us to build like something custom for them that, you know, brings them all in a weather station, we could definitely do that. That's kind of our capabilities, but mostly that's done for like airports.
All right, super informative.
So, James, one question I have, I can't remember, how often did you say the frequency was that it monitors the wind across a path?
We're measuring every like 3 seconds. We update every 3 seconds, so it's constant. So it's measuring the wind across that whole area. But it's we're taking, so what we're doing is every 0.3 seconds, we take 4,000 sample points. So it's an average of a bunch of different sample points. So when you think about, when you look through the air and you see heat coming off the street or a star twinkling, those are all like little pockets of air, right? So there's tons of, the air isn't uniform. And because it's not uniform, that's what we can actually see. That's what the technology is we're seeing that thermal turbulence. But because it's ambient air, the pockets might be a little bit bigger. And because we have a bigger detector, we can see that. Does that make sense?
Yeah. So how is it shown? Is there like a program that we would get to look at that says, okay, at this time, this is the direction, this is the wind speed or something like that?
Yeah, we can feed that, and it kind of depends on what you're using now and how you would want to see it. It comes off in like an ASCII string, and then you can bring that into a program, or we can develop a program, but we just haven't, you know, it depends on how you want to see it. So if you tell me I want to be able to see it and then look at a graph, I can do that, or I want to, you know, there's different ways that we can do it. It's a research tool. So there's a lot of different ways that we can do it. It depends on what you have in-house or what you want to use, and then what we can develop. We can definitely develop a tool that would bring in, you know, 3 different sensors and surround it and then give you an average or send out a certain report. Or we could feed it into another system. So we can work with you or with another company on how you take the data and then use that. But
Okay.
there's like, currently there isn't, I don't have a program off the shelf because I wasn't sure what exactly how everyone wanted to use it. We do have like the instance where they go into the aluminum smelters. We feed that straight into on this one, we feed that straight into an OPSIS system, and then they do all the calculations, and that's just averaging it. But if you wanted something more specific, like, hey, I can do windrows or something like that, we could definitely create something for you. I mean, that's in our wheelhouse that we could do. We just don't have anything standard that we say, okay, here's what it is, because we haven't determined how people might want to use the technology yet. Because there's most of the people, like I said, they're using it are the military, and they're doing weapons dispersion stuff, and some of that stuff's proprietary to them. But we could definitely develop something for you, or feed it into like, do you have like an ambient shelter currently?
No.
Okay. So we could, I'll talk to Tingy about it and see what makes sense. But if you have like a specific thing that you're looking for, what would you want to see, I guess?
I guess the wind direction is what I was most curious about.
Yeah, I mean, it'll give you the wind direction, whether it's going across that plane, and then how you, that comes off the back of the instrument. I can send you a manual that would kind of explain what that is. It's just a string of data, and then you would bring that into a program that would then display that and show that. So let me talk to them and find out what would be best, and then I'll kind of circle back and get everyone an answer on how we could do that.
Okay. Yeah, I was just curious, like how the data that it picks up is shown for like the end user.
Right. Most of this stuff is, it's a sensor, so that data is gonna be sent to another system that's gonna then display it. That's how most people have been using it, but in your case, it may be something that we could develop that would show like a windrose or something like that, a little program that would display that. Some of the people have like, I know like ESC has a data logger, and a few others have ambient data loggers that do stuff. We have windrows and stuff like that we do for airports, so I'm assuming we could also plug the data into that as well.
Mm-hmm.
So I'll let me talk to them, and then I'll come back and kind of explain how we could do that. But it's kind of, right now, it's kind of loose on how we can do it. So there's a lot of different ways that we could do it. But if we are more specific to know what we need to do, then I could say, when I talk to the scientists, they're used to dealing with NASA and stuff, so they sometimes don't I kind of thought this question might happen. So I can go back to them and explain to them, this is what we need to show. So let me do that, and then I'll get that to Steve.
Okay.
Okay. Hey, James, there's a question about, you may have explained, this is a question I'm reading off the chat line. You may have explained during a portion I missed, but you're measuring the magnitude of the component of the wind vector perpendicular to your optical path, correct?
Yes, the magnitude of the air going across that plane.
Okay, beautiful. If the wind was crossing the optical path at a 45-degree angle, the magnitude you measure would be equivalent to the sine or cosine multiplied by the wind speed?
I believe so. Some of that's over my head. But yes, the 45-degree angle, can you repeat that? Or can you send me that question?
Oh, it's in the chat line. If you click on the little conversation button on the upper right, you'll see all the questions, but I can read it again. For example, if the wind was crossing the optical path at a 45-degree angle, the magnitude you measure would be equivalent to the sine or cosine 45 degrees multiplied by the wind speed.
Yes. Hang on, I'm just trying to show hide participants. Where's the chat? I'm sorry, I'm trying to get to the chat, the conversation.
No.
So I'm going to copy that.
Yeah.
If the wind was a 45-degree angle, crosswinds. Yeah.
And hey, what we can do,
Yes.
we can put your answer in the chat line, and then people can come back and see your written answer afterward.
Right.
This is recorded and will be posted on the website. Okay, so thank you all very much. Great questions, James. A great presentation. I know I learned a lot, and I know this is a really, really valuable and relevant tool given the fence line monitoring and the prevalency of fence line monitoring increasing dramatically over the last few years, and I believe over the coming year. So this is a very timely presentation. Thank you very much for taking your time today and sharing your expertise.
Yeah, thank you. And I will get this answered on the one. I some of it's a little bit, I should have had Tingy on the phone. So but I'll get that answered for you.
No worries. Okay, and thank you to everyone that participated today. And with that, we'll stop the recording and end the call.
Thanks, Jim.
Thank you. Thank you. Bye.